Okay, let's finish looking at some class examples for the first derivative test. So example 2, determine the intervals in which the function is increasing and decreasing. Locate the relative extrema. So if we want to find out where the function is increasing and decreasing, we need to first find the critical points. So critical points come from the derivative. Now if I want to find the derivative here, I have to go through quotient rule. So quotient rule says f prime g minus fg prime. So f prime, 5x plus 2 becomes 5. G is the x minus 3 minus the original function up top, 5x plus 2, times the derivative of the denominator, which is 1, all over the denominator squared. We can expand and combine like terms. We get 5x minus 15 minus 5x minus 2. And that simplifies to simply be negative 17 over x minus 3 squared. No critical point from the numerator. Denominator will only produce x equals 3. So we put that x equals 3 on the sign line. Here I just chose two values to the left and to the right of the critical point. So if I plug 0 into the derivative, I'm going to get negative over a positive, which is negative. If I plug 4 into the derivative, I'll get a negative over a positive, which is still a negative. So I know my graph will be decreasing from negative infinity to 3, and then decreasing again from 3 to infinity. Again, anytime that we're testing to see what the slope is on the interval, we're always testing these values with the derivative function, right? We want to find out whether the graph is rising or falling in these intervals. We don't want to plug these values back into the original function, because then it'll tell us the y value, which in this case for this sign line will not be very helpful. Okay, we want to know the behavior of the graph in terms of whether it is rising or falling in these intervals. So here we have a function that's decreasing on negative infinity to 3 and from 3 to infinity. At 3 there's actually a vertical asymptote there, so that's why we have to also, that's a critical point that showed up from the first derivative. And it's decreasing simply because f prime is going to be less than 0. So therefore there's no relative extrema for the function because there's no change in signs, and also the critical point does not exist. Okay, example 3, make a first derivative sign line for the following graph of f prime. So this is the f prime graph, and we'll do probably some more examples a little bit later on. But if we're looking at the f prime graph, then the f prime graph, the way that we interpret the graph is going to be different, because the y value or the y-axis no longer represents the location of the graph. The y value now represents the slope of the graph. All right. So any part of the graph that is above the x-axis represents positive slope. Any portion of the graph that sits below the x-axis represents negative slope. So here, and also anything that sits on the x-axis represents where the slope is 0. So we can convert this to a sign line, and then from a sign line we can convert it to a basic sketch of the original f of x graph. So first off, easy part first, let's just pick out where the slope is 0. So we know the slope will be 0 at negative 3 and 2, and these will be also where our critical points are. So we put those on a sign line, negative 3 and 2. Now this portion of the graph, right, it sits below the x-axis, so we know the graph will have negative slope. And negative slope, we indicate that using a down arrow, right? Positive slope we represent using that up arrow. So in this region, we'll put a negative there because we see these values sit below the x-axis. Again, y values that sits below the x-axis, these all represent negative slope of the original graph. From negative 3 to negative 2, this region again sits below the x-axis, so we know that's a negative slope, so we put negative slope there. To the right of 2, we see the graph now it sits above the x-axis, so these are all positive slopes because these, again, the y values represent slope. So we want the graph to basically have this shape where it is falling, it hits a slope of 0, it keeps falling, hits a slope of 0, and then it rises at 2. So a graph may look something like this. Okay. We may not know the physical location of the graph because the graph may be higher up or lower, but at least we know the behavior in terms of its slope. We know it's going to be falling, hits a slope of 0 at negative 3, keeps falling, hits a slope of 0 at 2, and then rises after that.